The first talk is on batch bandit problems by Yanjun Han.
Great. OK. Show that. OK, great. OK, good afternoon, everyone. I'm Yanjun Han from Stanford EE. And today I'm going to talk about the multi-armed bandit problem with batch constraints. So this is a joint work with Zijun, Zhimei, and Zhengqing, all from Stanford. So what is a multi-armed bandit problem? It is a sequential decision-making problem where, given a time horizon t, the learner chooses sequential actions, known as arms. And at each time, the learner chooses an action or pulls an arm based on her historic observations and receives a random reward given that action. Her target is to maximize the cumulative reward given over the time horizon. Albeit very simple, the Bandit model fits lots of practical applications, such as spam email filtering, where the filter needs to learn adaptively the feature of spam emails. In dynamic pricing, where the retailer companies need to learn about the real-time demands, and in recommender system, which explores new items users may like and recommend them. And a key feature in the Bandit problem is the partial information in the space domain. That is, the learner receives a bandit feedback and only observes the reward of the pulled arm. For instance, at time 1, the learner has no information and chooses to pull arm 3. And then at time 2, she knows some partial information about arm 3 and then may decide to pull arm 2. And at time 3, she gathers some information from both arm 2 and 3 and decides to pull arm k and so on and so forth. So in other words, at each time, only one, the reward of the one pulled arm is revealed. In this work, we are going to study the batch multi-armed bandit problem, where the number of rounds of actively querying data is actually limited. In other words, we split the time horizon into m batches, and the rewards in each batch are not revealed until the end of that batch. The batch constraint also appear frequently in lots of practical applications. For example, in clinical trials, doctors can only conduct a small round of medical experiments, with each round consisting of multiple patients. And in crowdsourcing, it takes some time for a crowd to respond to the query, so there are also a limited number of interactions. And in reinforcement learning, sometimes switching between actions may have some cost, so it would also be preferable to learn in batches. And finally, the batch constraint is an interpolation between the two extremes, that is, the batch learning, where m equal to 1, and the full online learning, where m equal to t. So what's special in the batch constraint? So the key feature is the partial information in the time domain. That is, the learner only has limited rounds of adaptivity and receives feedbacks in batches. For instance, the entire time horizon can be split into 3 batches, and the rewards in each batch are simultaneously revealed at the end of each batch. Now here comes the mathematical formulation of this work. Let t be the time horizon, k be the number of arms. And consider a stochastic bandit setting where pulling arm I gives a Gaussian random reward with mean mu I and unit variance. And let star be the best arm with the highest expected reward. Delta I be the suboptimality gap of arm I. And a policy pi just consists of sequential actions determined by the observed reward before the current batch. And our target is to devise a policy to minimize the regret, which is defined to be the cumulative reward of this policy and the best policy in hindsight, which pulls the optimal arm at all times. To represent the batch constraint, we consider a time grid consisting of m time points, which can either be static, where it is fixed in advance, or be adaptive, where it can be sequentially determined by historic data. And our job is to jointly optimize or find a good policy and a time grid. We will consider 2 types of regrets motivated by the classical analysis of the multi-armed bandits by, for example, Vogel, Lai and Robbins, Audibert and Bubeck. And motivated by the first form, we consider the minimax regret, Well, one would like to minimize the worst case expected grad, while the suboptimality gaps can essentially be arbitrary. And motivated by the second form of the regret, we also would like to consider the problem-dependent regret, where each suboptimal arms are assumed to have a minimum suboptimality gap delta, and we somehow multiply this delta as a weight to the resulting regret. And note that in both scenarios, we have a technical arc-bound root k on the suboptimality gap to prevent a too large regret incurred by pulling a wrong arm once. And motivated by the classic analysis, it is immediate that in the full online case, the minimax regret is of the order root kt, and the problem-dependent regret is of the order k log t. Some studies consider the number of batches sufficient to achieve the full online performance. And the UCB, for example, the UCB2 algorithm proposed by our Bianchi and Fisher shows that log t batches sufficient to achieve the minimax regret in the online case. And Bianchi, Dekel, and Shamir show that log t batches are actually sufficient to achieve the full online minimax regret in the context of switching cost. The most relevant work to us is a study of the better two-armed Bandit case by Perturb, Regularize, Chomsky, and Stackelberg, who provides a complete characterization of the minimax and both the minimax and the problem-dependent regret in the two-armed case with a static grid. However, little is known for the adaptive grids, and the lower bound for adaptive grids are typically very challenging for adaptive policies. And the main result of our paper is to provide a complete characterization of the both the minimax regret and the problem-dependent regret in the general batched multi-armed problem setting. So here is the upper bound. There exist policies pi1 and pi2 such that the following upper bound hold, and in particular, log t batches become sufficient to achieve the full online minimax regret, and the log t batches are sufficient to achieve the full online problem-dependent regret. In other words, only a few batches are necessary in practice. The policy which achieves that the optimal regrets are actually quite simple. We propose the batch successive elimination policy, abbreviated as BASE, which works as follows. Given a time grid, we consider the set of active arms, which is initialized to be the set of all arms. And then in each batch, we just pull all active arms for the same number of times, estimate the quality at the end, and then eliminate all probably suboptimal arms from the active set. So here, the probably is quantified using confidence sets. In other words, the base policy is simply an alternation of pull and elimination. And we still need to propose the optimal time grid. And it turns out that the answer is the same as the two-armed case. So to minimize the minimax regret, we consider the minimax grid where the m's grid point Tm is proportional to the root Tm minus 1. And to minimize the problem-dependent regret, we consider the geometrical grid where the grid points are just a geometric sequence. As an illustration, when there are 3 batches, the minimax grid would be like T to the 4/7, T to the 6/7, and T. And the geometric grid would be T to the 1/3, T to the 2/3, and T. We also prove regret lower bound under the static grid. So this theorem shows that for static grid, the lower bound match the upper bound within logarithmic factors, which essentially means that the base policy cannot be essentially improved. The proof just uses a standard hypothesis testing approach, or called a max-min approach. Specifically, we just find multiple reward distributions and show that, no policy can perform uniformly well under these policies. The reason why we call this a max-min is that we first take the maximization over the hypothesis design, and then we take the minimum over all possible policies. In more detail, we'd like to construct hypotheses such that the following 2 conditions hold. The first is a large separation. That is, if a policy has a good performance under one distribution, it must have a bad performance under the others. The second one is a more important one, that is indistinguishability, which means that the learner cannot determine which distribution she is under. And to establish the indistinguishability, we prove the new lemma, which lower bounds the average test error under n arbitrary distributions by an average of the exponential pairwise KL divergence over the edges of any tree. So perhaps one would note that a more well-known lower bound for the left-hand side is actually the Fenton's lemma, but we remark that the Fenton's lemma will fail in this case, and the current form gives us the correct answer. And we also proved the lower bound for any adaptive grid, which is of an m² factor compared to the previous lower bounds. However, since the number of batches of interest is at most logarithmic in t, so our lower bound still matches the upper bound within logarithmic factors, which shows that, OK, adaptive grids are not essentially necessary. However, the previous max-min approach would break down to show this lower bound, even for a grid which is only randomized and does not depend on data. So to overcome this difficulty, we propose a min-max approach instead. So basically, we would construct the hypothesis after we see the policy. Yeah. In more detail, we would construct reward distributions, P1 to Pn, which do not depend on policy, but some events which does depend on the policy. And we first show that if any of the event has a non-small probability under the respective distribution, then the policy, we can construct adaptive hypotheses around this hypothesis and show that the policy incurs a large regret in the worst case. And then we show that the sum of the probabilities is non-small, which essentially shows that these events essentially cover the whole probability space. And combining these two lemmas, just gives the lower bound. So to conclude, in this work, we quantify the impact and show the optimal use of the partial information in both the time and space domains, and propose the base policy with optimal grids for the upper bound and alternative min-max approach for the lower bound with adaptive grids. I'd also like to point out some future directions. For example, how to remove the m² factor in the adaptive lower bound, how to generalize it to adversarial and contextual bandit, and more broadly, what are the general tools for limited round of adaptivity? So thank you for your attention, and please come to poster number 49 for more details. Thank you.
Maybe I'll ask a quick question. A quick question. So, what challenges do you foresee in extending this to, say, adversarial bandits?
OK. I think the main challenge to extend this work to adversarial bandits is to find a good oracle. To define a good oracle such that the oracle is not too strong to have a trivial result. If the oracle is too strong, we can actually easily show that, OK, the worst case regret is linear in the time horizon t, which is certainly useless. So we need to find a good definition of the oracle and find out what is the correct formulation of the adversarial contact bandits. Yeah.
Okay. Any other questions? All right. Okay. Let's thank Yanjun. So with this, we'll move on to the spotlight talk. So with the next four bandits, next four speakers, the next batch lineup, please.
OK. Hello, everyone. My name is Jayo. And today, I'm going to talk about how to tell whether the sample mean in multi-amp bandits are positively or negatively biased. And this is joint work with my wonderful collaborators, Aditya Radamas and Alexander from CMU. OK, so in stochastic multi-amp bandits, we have k arms. And if we prune arm, we observe a random reward from underlying distribution with unknown mean. And a typical goal of the bandit problem is to design an adaptive sampling scheme to maximize reward or identify the best arm. So typically, at every round, we choose an arm and we draw a sample. And at the next round, we choose another arm based on the previously collected data. And we draw another sample from the selected arm. And we repeat this procedure until we reach a stopping time tau. So although it is not a usually primary goal of the Bandit algorithm, after observing a bunch of data from the arms, we may have found that some of the arms very interesting to us. So we may want to estimate the mean of the underlying arm, which is interesting to us. And of course, we can do it by using the collected data. And the sample mean estimator would be one of the most popular choice of the estimator in practice. Among several characteristics of sample means, in this work, we focus on the sign of the bias of the sample mean of chosen arm at the stopping time. And this is not a new question. Actually, several researchers have been reported that in the multi-arm bandit setting, sample mean seems to be negatively biased in practice. And recently, Ni and her collaborators formally proved that sample mean is actually negatively biased for many popular choice of the algorithm, including Epsilon greedy, UCB, and Thompson sampling. However, I should emphasize that all previous works are about sample mean of a fixed arm at a fixed time. However, before seeing the data, actually, usually we don't know which one would be interesting to us. So I wanted to choose the target after observing the data. And also, this data collection procedure usually is stopped by a random rule, which is also depends on data. So in our work, we are studying the sign of the bias of sample mean of the chosen arm at the random stopping time. So in this setting, these previous works are not applicable. So we propose more general, but even simpler condition by which we can tell the sign of the bias under all these kinds of adaptivities in sampling, stopping, and choosing. So for each aspect of adaptivity, we show that the sample mean of the chosen arm at the stopping time is negatively biased under optimistic sampling, but under optimistic stopping and choosing, sample mean is actually positively biased. So more generally, let's think about the following function from the sample of arm to the indicator of the selection event divided by number of samples. We've showed that if this function is increasing, then corresponding sample mean should be positively biased. And if this function is decreasing, then the sample mean is now negatively biased. So this result is agnostic to algorithm and underlying distribution, so you can use your own favorite algorithm to apply this condition to any distribution. And also this is very general, so it includes the previous work as a special case. And as an important implication, this theorem implies that under best time identification or many sequential testing procedures, the sample mean of the chosen arm at the stopping time is actually positively biased. So we should expect some overestimate when we use the sample mean estimator. Thank you for your listening. For more intuition and more detailed explanation, please visit our poster. Thank you.
Hi. So I'm going to present a joint work with Vianney on the topic of synchronization in multiplayer multi-arm bandits. So as a reminder, here is a single player stochastic bandits game. So at each time step, a player pulls among a set of arms and gets the associated reward. Now let's have a look at the multiplayer bandit setting, where several players pull among a common set of arms at each time step simultaneously. If all these players pull different arms, they all get the associated rewards. However, as soon as several players are pulling the same arm, we say that a collision happens, and in this case, they all get a null reward. So in the following, we are looking at the setting where the players both observe the indicator whether or not there is a collision and the true reward. In this problem, we measure the performance in terms of total welfare, meaning that the players are assumed to be collaborative. In the easy centralized model, a meta agent is able to control all players' behaviors And in this case, it is a well-known result that the logarithm scales as log t times the sum of the inverse of the suboptimality gaps. So this is a classical Bandit result. And in the harder setting that we are considering, where the players are independent and cannot communicate to each other, it was thought for many years that an additional m factor was added in the regret, where m is the number of players involved in the game. So this was rather instinctive. It just means that each player has to individually explore as much as the meta agent in the centralized case. But what we showed with the SIGMAB algorithm is that there is no m factor actually in this decentralized regret, meaning that the decentralized case is not much harder than the centralized one. So how is such a result possible? SIGMAB actually comes from a simple observation that the collision indicator can be seen as a bit sent from one player to another one. Abusing from this observation, we can enable communication between the players, who will be able to send to each other the empirical means. And by doing it in binary, the communication cost remains negligible, thus making the problem almost centralized. And the players will then run a successive accept and reject algorithm, alternating between exploration and communication phases. However, such a result is not really desired, as SIGMAB relies on unrealistic protocols. It actually abuses a loophole from the model, and our belief is that this loophole is the synchronization, which assumes that all the players start at the same time. This is indeed what allows the players to communicate, because they all know when to send messages to each other and receive these messages. So our claim is to remove the synchronization assumption and to consider the harder dynamic model, hoping that it will overcome this loophole. So we suggest for this to consider the dynamic model, where all players start at different times, but still end at a common time. So this remains a strong assumption here in our model. And even in the harder case, where the players do not observe whether or not there is a collision, but only the true reward, we provide a new algorithm, so DNMAB, with a logarithmic regret. So it does not rely on communication protocols anymore, but it relies on a simple policy where each player at each time step either sample uniformly at random or exploits some optimal arm until the end. So despite being simple in terms of policy, its analysis is rather intricate. So if you want to know more about this paper and this work, you can come and discuss about it at poster 11. Thank you.
Hi, I'm Kira, and I'm going to present some joint work that I've done with Stefan Grunewater at Lancaster University. And this is on recovering bandits. So bandits are often used in product recommendation. So here we take as an example a furniture website. And here we have a user who buys a sofa. And then what we want to happen afterwards is they get suggested lots of other items which might go nicely in their new living room. So for example, a table or a plant. However, often what actually happens is after they buy the sofa, they go back on the website and they're suggested a load more sofas. And this isn't ideal because once you buy a sofa, you generally don't really want another sofa for another couple of years. And so a natural question to ask is why this happens. So when we use Bandit algorithms for recommendation, what we do is we model each item or group of items as an arm and then apply a classical Bandit algorithm. All these classical algorithms are built under the assumption that the reward distributions of the arms are stationary. So this means a good algorithm will learn to play the optimal arm, and it will learn to play that continually. So for example, back to the furniture setting, that means that the good algorithm for the classical bandit problem will keep suggesting the sofa, even though what we actually want to happen in practice is for the algorithm to wait until the user might want another sofa and then suggest it later. And this is a problem we tackle in recovering bandits. So more specifically, we assume that the reward of each arm is a function of the number of time steps since the arm was last played. So in the figure here, on the x-axis, we have the time since last played, and on the y-axis, we have the reward. So if each colored curve represents a different arm. So if we just consider one arm here, say, for example, the red one, at time 0, so when it's just been played, its reward is low. But then as time goes on and we don't play that arm, its reward will increase. So as we keep not suggesting a sofa to a user, the reward from suggesting them a sofa will increase. And we take a Bayesian approach and assume that these models are smooth enough to be modeled by a Gaussian process. This allows us to get good estimates of uncertainty, but it also means that we can consider a wide range of recovery functions that don't necessarily have to be increasing. This problem is harder than the stationary bandits problem because instead of just estimating a single mean for each arm, we have to estimate these entire recovery functions. It's also quite difficult to define an optimal policy in this setting. So particularly, selecting the arm with the current highest reward is not going to be optimal. So if we have two arms whose mean rewards are very similar at time t, but we know that if we don't play arm 2, its reward will increase, whereas the reward of arm 1 will stay the same. What we want to do is we want to play arm 1 first and then wait until the reward of arm 2 is recovered. So building on this, we want to try and find sequences of D plays that will select a good sequence of D actions to maximize the reward over the next few steps. And we define the corresponding regret with respect to the best optimal policy that looks D steps ahead. So obviously, the best choice of D would be to pick it as the horizon T, but this is computationally infeasible even if the functions are known, so it's not possible to find this optimal policy. So the good news, though, is that we can show that for relatively large D, the best D-step look-ahead policy will behave nearly as good as the optimal policy. So now that we've defined our optimality criteria, we present modifications of UCB and Thompson sampling that exploit the properties of the Gaussian processes to select good sequences of D arms. In particular, Gaussian processes are nice because their posteriors are Gaussian, and then when we have a sequence of arms, adding these Gaussians will also be Gaussian. So we can construct an upper confidence bound on them, or we can sample from the posterior for Thompson sampling. Both of these algorithms achieve Bayesian D-step look-ahead regret of square root dkt, which is just a square root d factor worse than algorithms for the stationary bandit problem. However, these algorithms are not super computationally efficient. Because we're looking at sequences of D arms, we have k to the power of d sequences that we have to consider at each time step. However, we provide an adaptation based on optimistic planning to speed up this search, and we can guarantee theoretically that this will improve the computational complexity and still return a near optimal sequence. Experimentally, we see that our algorithms perform as expected. So here, each plot is a different arm, and the red curve represents a true recovery function. The crosses are our observations, and we see that these crosses are mainly at the peaks of the curves. And this is promising because this shows that our algorithms are learning to play the arms when their rewards are highest, so they're learning the dynamics of a recovery structure. We also show experimentally that our algorithms outperform other methods, and that the optimistic planning procedure is indeed more computationally efficient. So for more details, come to the poster tonight, number 9.
Cool. Yeah, so I'm Dylan Foster, and this is a joint work with Akshay Krishnamurthy and Haipong Luo. And it's about how do we provide model selection guarantees for interactive learning problems, and in particular, contextual bandits. So, oh, cool. All right, great. All right, so let me recall the sort of model selection guarantees in statistical learning, what these look like. So imagine we have a large hypothesis class, script F, and this is going to be a very large class, possibly too large to even be learnable. But what we're going to assume is that it has a nested structure. So it decomposes as a sequence of nested hypothesis classes, and we'll assume that the Bayes hypothesis lies somewhere in the middle here, say M star. It lies in the M star class. So in this setting, model selection algorithms provide the following guarantee. They guarantee that the learner has risk that is at most that of the Bayes optimal predictor, plus a generalization error term that scales only with the size of the smallest subclass that contains it. So this is obviously an easy guarantee to achieve if we knew the smallest subclass in advance, but we're getting this with no prior knowledge of the optimal subclass, and we're only paying a log m star factor to do this. And so what we wanted to understand in this work is whether it's possible to attain this type of guarantee in contextual bandit learning, where examples arrive one by one rather than in a batch, and where we have partial information, so the actions we take influence what data we see. So let's think about whether this should even be possible. So in the statistical learning setting, like I just described, the algorithmic principle that sort of achieves model selection guarantees is structural risk minimization. And really all this does is run an algorithm for each class and then aggregate these while penalizing for complexity of the class. In online learning, which is sort of in between contextual bandits and statistical learning, it's still possible to attain this type of guarantee. You just run mini algorithms for each class and aggregate them using exponential weights. And as long as you turn the learning rate, you get a similar guarantee to the one we had on the previous slide. But in contextual bandits previous to this work, we're aware of essentially no good results, no model selection results, even if we restrict ourselves to specific types of function classes, and even if we're okay with suboptimal rates, say suboptimal dependence on the number of rounds t. And sort of the key issue here is that this standard kind of algorithmic approach, the run an algorithm for each class and then aggregate, this doesn't really work at all in the contextual bandit setting because the contextual bandits kind of breaks the feedback model here. Like each of your sub-algorithms wants to pull a different arm, but you can only pull one at each round. So with this in mind, our guarantee is the first model selection result for linear contextual bandits. And let me describe the setting here before I talk about the result. So the setting is as follows. We're going to play t rounds, and at each round we'll receive a context. We'll take an action, one of k actions, so we're in the finite action setting, and then we'll see the loss of the action we took, and we'll be looking at regret compared to get the best policy in hindsight. And so for the linear setting, what we're going to assume is that the mth policy class can be looks like the set of all linear functions over a feature map phi m. And then we're going to make the realizability assumption, which will just state that the m*starth class, so the class with the Bayes, we're going to assume that there's some weight function so that the conditional expected loss in this setting looks like a linear function of the m*starth feature map. And of course, this implies that the optimal policy is itself just the argmax for this linear function. All right, and so in this setting, if I knew the optimal class in advance, like if I knew m star, then I could just run linucb, and this would get root dm star t regret. And so what we want to see is what can we get without knowing this in advance. Okay, so our main theorem is to provide two different guarantees. So both guarantees work with no prior knowledge of the optimal dimension dm star. So the first gets dm star to the 2/3 t to, dm star to the 1/3 t to the 2/3 regret, and the first gets root t times dm star plus t to the 3/4 regret. So the second one of these bounds is the same as the linucb bound, except it has an additional t to the 3/4 factor. And I want to stress that both of these can probably be improved, which is a nice open problem. But I want to emphasize that these are like bona fide model selection guarantees in the sense that they provide sublinear regret whenever the original problem is learnable. Meaning, if we knew dm star and dm star is less than t, these algorithms will give sublinear regret. And in the remainder of the talk, I just want to sort of sketch how this is achieved. So the basic idea is pretty simple. All we're going to do is start off by running a contextual bandit algorithm, say the optimal algorithm for one of the small classes, but we'll allocate some fraction of the rounds to explore uniformly, and we'll use the data from those rounds to test if we could benefit by moving on to a bigger class. Okay, but the key challenge here is how do we test if it would be good to move on to a bigger class without simply learning that class? And this is an important issue because if it turns out that our current class is good, we don't want to ruin our sample complexity by moving on or by using a lot of data to test if a bigger class would have been good. So the key trick that allows us to do this is that for the linear setting, it's possible to test if the best in class loss is good with much fewer samples than it takes to actually learn the best policy for a given class. So it turns out that for this linear realizable setting, it suffices to just estimate this sort of gap between the optimal regression functions for class I and class J if I'm trying to compare these two classes. And of course, if you're going to use like the plugin estimator to do this, like if you're going to use least squares, this would have sample complexity scaling as dj over n, where gj is the bigger class. But basically, by using a more sophisticated estimator that builds on these techniques introduced by Dicker, we can get sample complexity that scales as dj to the 1/2 over n. And this leads to the trade-off that gives it's in the previous slide. So if you want to learn more, you can check out our poster. And I just want to say this raises a lot of new open questions. And the main one is just, for the general setting, can you get model selection guarantees? So either positive or negative results there would be very cool, I think. Thanks.
All right, so we'll move on to the second oral in this session, and it's by John Schneider on strategizing against no-regret learners.
All right. Hi, everyone. I'm going to talk about strategizing against no-regret learners. This is joint work with Yuan Deng and Balasubramanian Sivan. So this is a talk about games. So we're going to talk about two different ways you can play games. So two types of agents which are commonly studied are strategic agents and learning agents. And strategic agents, this is the classical economics rational self-interested agent. They play to maximize their expected utility. But in order to do this, they need to completely understand the game. If there's types, they need to have priors over the other player's types or strategies, and it can be computationally hard to play this way. On the other hand, you can have learning agents, which use an online learning algorithm to learn how to play over time. For example, multiplicative weights or EXP3. And the common thread here is that these, like learning agents, maybe they'll have some low regret guarantee. We'll look at low regret learning agents in this talk. So what do we understand in general? Well, we have a good understanding of what happens when you have games where lots of strategic agents play each other. This has been studied by economists for like the past 150 years. In this case, into the mic? Okay, is this better? Great, so this is covered by classical game theory. We have theorems which say that they'll play according to some equilibrium, for example, a Nash equilibrium. And these equilibria might be hard to compute, but you can play according to them. All right, on the other hand, if you use your favorite learning algorithms, we also have some understanding what happens if you have a game where everyone's using a learning algorithm to learn how to play. We know that over time, on average, they'll converge to these sorts of equilibria, whether they're correlated equilibria or coarse correlated equilibria. We have some understanding of what happens here. What we don't understand very well is what happens when you have mixtures, like combinations of strategic agents and non-strategic agents playing together. And in fact, what we don't even understand very well is just this simple case, where you have one no-regret learner and a strategic agent playing against it. And this is going to be the subject of this talk. Basically, what's the best thing to do as a strategic agent if you're playing against a no-regret learner? How should you strategize? So, very quickly, there's been a lot of prior work recently on learning in strategic settings, but perhaps the most directly relevant prior work is this work on online auctions, which studies this problem for a very specific game of a seller selling to a no-regret buyer. And Braverman et al. Investigate how to design auctions where the bidders are bidding using no-regret learning algorithms. And the upshot of their work and the upshot of this work too is that there's important differences between what happens when you have no-regret bidders and strategic bidders. And we'll see this in the next few slides. So the setting here is you have a repeated game, so just a repeated bimatrix game. Here are the actions for the first player on the left, the actions for the second player on the right, and this pair of values is the utility for the left player and the utility for the right player. And they play this game over a bunch of rounds, T rounds, and at the end of the game, their utility is maybe the sum of utilities so far. And we'll look at this case where one player, like the left player, for example, is us. We're like a strategic optimizer. We can choose to play however we want. We want to maximize our long-term utility. But the second player, the left-right player here in this case, is running a no-regret learning algorithm to choose how to play their actions. So we've seen a couple talks on Bandit algorithms so far, but just to be on the same page, by no-regret learning here, we just mean that no-regret learner is using a no-regret learning algorithm to choose their action every stage, and an algorithm is no-regret if, in hindsight, their selection of actions performed as well as the best possible fixed action in hindsight. So, returning to the problem, let's say you're playing a game against a no-regret learner. What you do? So the first thing you can try to do is play a fixed strategy, a fixed mixed strategy for all t rounds. This guarantees you at least the Stackelberg value of the game. So what's the Stackelberg value? So just as a quick detour, games have Nash equilibria, which is where no player wants to deviate, but in the Stackelberg value, in the Stackelberg equilibrium, one player gets to move first. So in this case, that's us. So we can choose to commit to playing this down action, and then the second player, the learner, will learn to best respond. In this case, they'll learn to play the right action. And in this case, I think down is probably the best action for us. So this square, 2, 1, is the Stackelberg equilibrium, and we get a Stackelberg value of 2. So by playing the best fixed strategy, the optimizer can guarantee themselves at least the Stackelberg value times t minus some little of t term, perhaps. So the natural question here is, if the learner is running a no-regret learning algorithm, is it possible for us, the optimizer, to get anything larger than the Stackelberg value? And the answer is yes, we can. So yeah, it's phrased the opposite way here, but you can get more than the Stackelberg value. And so we're going to talk about a specific type of no-regret learning algorithm, or a specific class of no-regret learning algorithm called mean-based algorithms. So mean-based algorithm is an algorithm which almost always plays the action that performs the best historically. It best responds to the best response to history, essentially. And many no-regret algorithms are essentially mean-based. So EXP3, multiplicative weights, follow the Perturb leader, et cetera. And this class of algorithms was also studied in this prior work mentioned by Braverman et al. So what we can show is that if the no-regret learning algorithm is playing a mean-based algorithm, then in some games you can do much better than the Stackelberg value. So in this game on the slides, the Stackelberg value is 0. The exact equilibrium is when we play half up and half down, and the top player plays right. But it's possible, if we change our strategy over time, to get something much larger than 0. We can get 2t minus low of t. And the idea for this is that, yeah, you want to change your value or action over time to take advantage of the fact that the other player is sort of playing the best response to the historical best action. So here you can see like the cumulative utilities of the 3 actions for the learner, the left action, middle action, and right action. And what you do is you do something like we play one of our actions for the first half of the rounds and the other action for the second half of the rounds. And by doing this, we convince the learner that one of the actions is a lot worse than it actually is. So for example, at time 2/2, what we do is we switch from playing up to down. And if the learner could react immediately, if the learner was completely strategic and understood what we were doing, the learner would learn to play middle, because that gives them the highest utility when we play down. But since they're best responding to history, the learner plays, I think they play right still, and then we can get 2 per round in the second half of the game, and we get much more than the Stackelberg equilibrium. Okay, so given this result, you might ask, can the optimizer always get much more than Stackelberg equilibrium in every game? I mean, there's some degenerate games, but what's the limit of this phenomenon? And specifically, here we sort of relied on this fact that the learner is best responding to history. Is this necessary? So in other words, are there non-mean-based learning algorithms that prevent this from happening? And the answer to the second question is yes. So there are some cases where we can show that the optimizer, us, we can't get more than the Stackelberg value every round. So one simple case is if the game is zero-sum or constant sum. In this case, you can show that the Stackelberg equilibrium is the Nash equilibrium, which is just the minimax equilibrium. And no matter what we do, we can't do better than what we get under the min-max theorem. But perhaps more interestingly, if the learner is running a no-swap-regret learning algorithm, and this is like a stronger notion of no-regret that can be constructed from no-regret by a clever reduction, you can show that if the learner is using a no-swap-regret learning algorithm, we can't get anything larger than the Stackelberg value every round. And this is interesting. This means that basically there is some sort of problem with mean-based learning algorithms which allows them to be strategized against, which no-swap-regret fixes. And then like a simple corollary of this is that if the learner has only 2 actions, you can't get anything better than the Stackelberg value because in this case, no-regret and no-swap-regret are the same. Okay. So this just summarizes what we know. In general, the optimizer can guarantee themselves at least the Stackelberg value every round. Their utility is upper bounded by the Stackelberg value plus maybe a little of t. Under these specific cases, the game is constant sum, the learner has only 2 actions, or the learner is running a no-swap-regret learning algorithm. And the general takeaway is that for some reason, no-regret algorithms can be strategized against, and no-swap-regret algorithms prevent this phenomenon. So there's still many open questions, many phenomena here we don't understand. One like very concrete open question is what's actually the best thing to do if the learner is running a mean-based learning algorithm? So we characterize this in this paper via reduction to a control problem, but we don't know how to computationally solve this. We don't even know if the best policy is computable. And there's many questions about what happens when you have multiple agents or in Bayesian settings. Anyways, thank you, and come visit us at Poster 222 this afternoon.
One quick question, maybe?
Sure.
Okay. Speaking of this. Yeah, so, wow, okay, it's a little too loud. Okay, so if you use a no-swap regret algorithm, the little O term is going to depend like polynomially with the number of actions, right? So if you wanted logarithmic dependence on the number of actions, do you think you could achieve better than, no better than Stackelberg?
It's a good question. This also comes up when you try to think about what happens in the Bayesian setting, where number of types or contexts comes into play. We don't know. Yeah.
Hi, John. Can I ask a question?
Oh, hello. Yeah.
Here. Sorry. Okay. So. Do these characterizations change if you have stronger than regret guarantees? For example, if your comparator is allowed to make k-switches and such? Because your example seemed to rely on like us as the strategic learners switching between 2 actions at a certain point.
Yes, that's another good question. This also came up in the previous Braverman et al. Work. We don't know what happens in this case for general games. We know for the selling to a bidder game that you can construct bad examples even under things with like low constant switching regret. Yeah.
Thank you.
Okay, let's thank John. And we'll move on to the next batch of Spotlight speakers. So just start coming up.
Hi, everyone. Thanks for coming. My name is Gautam Goel. I'm a PhD student at Caltech. Today, I'll be talking about some joint work with Yiheng Lin, Haoyun Sun, and Adam Weirman. Traditionally, online learning has focused on regret minimization, where the goal is to design online learning algorithms that quickly converge to the best fixed action. So, for example, in a lot of the talks we've seen in the Bandits, the goal is to figure out what is the best single arm. I want to argue that this framework fails to capture many interesting real-world examples. So, for example, consider portfolio optimization. there is no single optimal golden portfolio which all investors are trying to converge to. Instead, investors are trying to maximize their long-term rewards in the face of changing market conditions. Similarly, in control, there is no single control action which is the best in every scenario. The whole point of control theory is to design systems that dynamically respond to a changing world. Another thing these two examples have in common is that they both prominently feature switching costs. So for example, in portfolio optimization, every time you execute a trade, you pay some trading fee. And in adaptive control, there's always some control cost which you incur as you transition your system from one state to another. So what this talk is about is how do we design online learning algorithms that can adapt to dynamic environments and account for switching costs. So the model we're going to look at is online convex optimization with two modifications. So firstly, I'll assume that the online learner has one-step look ahead, meaning that he gets to observe the cost function ft before picking the point xt. And I will also assume that in addition to this hitting cost, ft of xt, the learner also pays a switching cost, which I'll take to be the square distance of his current point xt from his previous point xt minus 1. So this switching cost sort of penalizes the learner for changing his action between rounds. So I guess, pretty much every talk in this session has focused on regret minimization. We're going to take a different perspective. So our goal is to minimize competitive ratio. So competitive ratio is the ratio between the cost incurred by our online learner and the cost of the best dynamic sequence of actions. I want to emphasize that we're competing with this dynamic sequence, not the best fixed action. And we have a new algorithm called online balanced descent. This is the first algorithm which has bounded competitive ratio. So there are two key ideas in online balanced descent. So the first idea is that at every step, I should always pick a point, which is the projection of my previous point, xt minus 1, onto some level set of the current cost function ft. So in this diagram, suppose I start off at the point xt minus 1. The cost function ft arrives. It has these ellipses as its level sets. And I decide to move onto this dark black ellipse, this dark black level set. Which point should I pick? Well, every point on this level set has the same hitting cost, because they're on the same level set. So clearly, I should pick the point xt, which is closest to the previous point xt minus 1, because that way I can minimize my switching cost. So clearly, we've agreed that the point I pick should be the projection onto a level set. The question is which level set? And OBD says that we should pick the level set so that the switching cost and the hitting cost I incur are balanced. So that means that they're roughly equal. The intuition here is that because I don't know the cost sequence in advance, I don't know whether I should invest my work in minimizing my hitting cost or whether I should invest my energy in minimizing my switching cost. So I'll hedge my bets, and I'll sort of put equal work in both categories. And the main new result is that we show that this OBD family of algorithms is the optimal family. So in particular, we construct a new lower bound on the competitive ratio achievable by any online algorithm. And we show a new version of OBD, which we call ROBD. And we prove that it exactly achieves this optimal competitive ratio all the way down to constants. Okay, so in that sense, it is the exact optimal algorithm all the way down. Okay, so I'd like to begin wrapping up. I would like to mention some new work that connects OBD to statistics and control and non-convex optimization, kind of a lot of hot topics here. So if you're interested in this new work, come talk to me. Come see our poster. It's number 50. I'll see you there.
Hey everyone, I'm Ren Yuan from Oxford. Today I'm going to introduce our paper on learning in generalized linear contextual bandits with stochastic delays. This is a joint work with Zheng Yuan from NYU and Jose from Stanford. Let's take this example of online advertisement recommendation problem. So every time when the user opens a new web page, the recommendation engine will try to put some advertisements on the web page by utilizing this user's feature and personal information. And the single recommendation is typically on the time scale of minutes or second. But however, the user's feedback, which is the purchasing behavior, happens less frequently, which is typically on the time scale of days, weeks, or even months, which means the feedback is usually delayed. Of course, there are other online decision-making problems that have this same delay feature. For example, the medicine recommendation in clinical trials or robot advising in financial investments. Now the question is, how should we do recommendation in such scenarios when delayed feedback are involved? So our approach is to model this problem as a contextual bandit problem and put minimum assumptions on the delays. For example, we allow our delay to be unbounded and near habitual. So this is the setup of our problem. We run these experiments for T rounds, and the learner can take actions from K different options. So in each round T, the learner will observe K different feature vectors in dimension D of different actions. And the learner will take an action AT based on historical information and the current feature vectors. Once the action is taken, there is an associated reward which will be reviewed later on in round T plus dt. And the dt here is our delay. We assume the delay is stochastic, possibly correlated, and unbounded. The underlying relationship between the feature vector and the reward satisfies this generalized linear model. So theta star here is the unknown true parameter that we are interested in learning. Epsilon t is the sub-Gaussian noise in the current round, and g is the inverse link function that connects the feature with the reward. So for this problem, we propose a UCB type of delay-adapted algorithm. And for our algorithm, the confidence response depends on delays in real time. And in each round T, we select a subset of samples to calculate the estimator for theta star using the maximum likelihood estimation. So for this algorithm, our regret bound achieves this order with high probability. So we can see that the leading term doesn't depend on delays. However, there's some interesting additive effect from the delays. So all this algorithm and the analysis works for infinite number of arms. In the special case, when we have finite number of arms, we can further tighten this regret bound in feature dimension D from D to square root of D. The idea is to combine the base subplane UCB decomposition with their careful handling of the delays. So for example, in each round, when we try to construct the estimator for theta star, we construct a biased estimator for it. So if you are interested in our work, please come to our poster session. We are poster number 2.
Hello, everyone. I'm Yunwan. Today, I will present our work on optimal stochastic and online learning with individual iterators. This is a joint work with Peng Yang, Ke Tan, and Ding Xuanzhou. In machine learning, we often want to solve an optimization problem of a composite structure, where the objective function consists of a date fitting term and a regularizer, which we assume to be convex. Our aim is to identify a model with a small function value. We apply stochastic composite Miller descent to solve this optimization problem, where we introduced a strongly convex Miller map, which is able to induce a Bregman distance on different points. At each iteration, we built a temporary objective function by replacing the date fitting term with a first-order approximation as a current iterator based on a randomly select example, and use the Bregman distance to make sure that the next iterator not far away from the current iterator. This framework covers many popular algorithms, for example, stochastic gradient descent. Since we build a sequence of iterators, there are many strategies to build a model for the final prediction. For example, we can take the last single iterator for prediction. We can also take a uniform average or a weighted average of the iterators for prediction. We can also take a uniform average over the last second half of the iterators, or randomly select a single iterator from a distribution over the iterator sequence. However, these strategies either produce models with suboptimal convergence by involving an additional logarithmic factor, or requires an averagist operator to achieve optimal convergence, which, however, destroys the sparsity. Indeed, an average of some sparse models can be no longer sparse. This motivates us a question: can we develop an algorithm with optimal rate and sparsity? Our idea is to identify a single iterator for prediction based on the one-step progress inequality of the algorithm, which measures how the iterator would move toward an optimal model within a single update. If we set W as the optimal model in the one-step progress inequality and can show that the difference between the Blackman distance of the two associated Blackman distance is small enough, then we can show that this convergence rate decays as a linear function of the step size, which is optimal if we take a standard choice of step size. That is, we build a sufficient condition for a single iterator to be optimal. By non-negativity of Blackman distance, we can always find a time index such that the difference of the two associated Blackman distance is smaller than a time, which guarantees the sufficient condition for optimal convergence. Then we can output this single iterator. This strategy, however, involves the optimal model, which is unknown to us. In practice, we can replace it by a surrogate with a small function value. Our algorithm consists of two stages. In the first stage, we perform the standard stochastic composite Miller descent and take a surrogate as a surrogate. In the second stage, we use this surrogate to set a single iterator for which the difference between the two associated Blackman distance is small enough, and we output this single iterator for prediction. We can also extend our algorithm to the online learning setting, where we do not require the information on the number of iterations. Under my assumption, we show that our algorithm can achieve optimal convergence in both convex and strongly convex cases. We apply our algorithm to tomography reconstruction with a least square objective function value, which involves a city measurement matrix and a noise measurement vector. The solution is a sparse image. We applied randomized sparse customized algorithm, which is a specific stochastic composite Miller descent with a Miller map and the least square loss function. Our experiment results show that our algorithm can outperform baseline strategies by achieving a faster training speed as well as in achieving a sparsity. For more information, please come to our poster 164. Thank you for your attention.
Hello, everyone. My name is Young from the University of Michigan. This is a joint work with Jacob Abernathy, Chansu Lee, Audra McMillan, and Ambush Tewari. So in this work, we provide a new perspective from differential privacy to propose and analyze online learning algorithms. I want to emphasize that our goal is not to develop an online learning algorithm that preserves privacy, but instead, we want to make a claim that DP-inspired stability notion is very well suited to analyzing online learning algorithms. More precisely, we define a new stability notion which provides a unifying framework to analyze existing and new online learning algorithms. This framework is especially useful to prove first-order regret bounds. So this is our setting. We are interested in the adversarial online learning, and we studied both the full information setting and the partial information settings. The learner's goal here is to minimize the expected regret. Here, L star is the minimal possible loss of a fixed action. The zero-order bound tries to prove the regret is sublinear in T, the time horizon, or the first-order bound tries to prove sublinear in L star, which can be much stronger in case L star is small. So our setting is abstract enough to cover many different prediction problems, including convex and linear optimization, or expert problems and partial information settings, including multi-arm bandits and bandits with experts, so-called contextual bandits. In the meantime, differential privacy cares about data privacy, and given a randomized algorithm A, we want A of S and A of S prime are similar, given S and S prime are only different by a single entry, so that the user is difficult to make inference about the data that we have. More formally, people are using the delta approximated max divergence to measure the difference between two distributions. And we say A is epsilon delta dp if the divergence between A of S and A of S prime is less than delta. So the main intuition here is that in online learning, we know the follow the leader type of algorithm performs badly in general. However, the follow the perturb leader or the regularized leader can do much better. And these latter two are more reluctant to change their decision rules, and that makes us to think about this differential stability. And we say A is differentially stable if its consecutive actions are close in certain divergence. This is our key lemma. Let's say we want to analyze the regret of some algorithm A. Then we construct a new imaginary algorithm A plus, which just predicts xt plus 1 at time t. And that means A plus observed the loss LT before making its prediction. So it's sort of cheating, and in that way, the regret of A plus can be very, very small. But if we know that our original algorithm A is differentially stable, we can bound the regret of A using the regret of A plus using this inequality. Then tuning epsilon and delta, we can easily show the first order regret bound. Furthermore, it is not that hard to come up with differentially stable algorithms because we already have lots of algorithms in DP literature. So this is one good example for online convex optimization. So we have object perturbation algorithm from DP literature, and we just apply this algorithm at each time. That will automatically ensure this algorithm is differentially stable. Then we apply key lemma tuning epsilon and delta to prove this algorithm has a first order regret bound. As I said, this can be applied to many different prediction problems, and it can be used to prove zero order or first order regret bound, or even proposing a new algorithm. So please come to our poster number 53, which starts right now. Thank you very much.